Hello everyone, welcome back to our generator protection playlist. In this video we will be focusing on the frequency protection, specifically the 81 over frequency and under frequency protection function and how they work together with voltage related protection. So frequency deviations can stress both generators and turbines, causing mechanical stress, overexcitation or even system instability. We will explore the operation of this protection, their typical setting and how to test and verify them using the OMICRON Test Universe modules. You will see how under and over frequency stages as well as related voltage tests are tested step by step to ensure the relay responds correctly and reliably. So let's dive in and get started. So the frequency protection in the beginning, or the 81 in the ANSI code of protection, protects the generator and turbine from operating beyond their safety frequency limits. So both can only tolerate a limited range of deviation, with low frequency reducing generator output and posing risks of mechanical responses in the turbine blades, especially in the steam and the gas units. So the frequency protection must be coordinated with the automatic load shedding scheme to prevent system collapse or equipment damage during the abnormal conditions. So the under frequency can cause higher load currents, overexcitation, and turbine stress, while the over frequency may lead to over voltages, particularly in the hydro turbines. The hydro plants, the turbines can handle a wider frequency variation, so under frequency protection is often unnecessary, but the over frequency protection remains essential as a backup or to replace the mechanical overspeed devices in case of governor failure. So you can see from the screen here the typical setting of the relay, Siemens relay 7UM62. So you can see here the over and under frequency protection setting. You can see the frequency pickup of 49.80 hertz. Here is the under frequency with the time delay equal to 20 seconds. Also the stage 2 of the under frequency protection is equal to 47 hertz with time delay equal to 10 seconds. So stage 1 is considered as a warning or alarm. Stage 2 is considered as a trip. By the same way also for the over frequency stage 1 and stage 2. So stage 1 is set to 50.2 hertz with time delay equal to 20 seconds. And stage 2 is equal to 52 hertz with time delay of 10 seconds. And here is the minimum required voltage for operation, which is equal to 65 voltage. And we will see how to test all of these parameters in the next few slides. So starting off testing of the under frequency pickup value. So when testing the under frequency protection or frequency under stage 1, the test universe ramping module is used to gradually decrease the frequency until the relay picks up at the expected set point. Before starting, make sure the local hardware configuration is correct. So we need a 3 voltage output should be mapped as a phase to neutral voltages, and the start signal of the under frequency or the over frequency stages must be connected to a binary input of the CMC. So during the test, nominal voltage must remain applied throughout the entire sequence to prevent unwanted operation of the under voltage protection or blocking the frequency function. So depending on the protection scheme, it might also be necessary to simulate additional substation conditions such as circuit breaker closed signal to disable any blocking of the under frequency protection and ensure the relay responds correctly to the frequency drop. So you can see here from the ramp test we have 4 ramps, so ramp 1 and ramp 4 with the nominal frequency, just to allow the relay to be resetted after ramp 2 and ramp 3. And ramp 2 here we will decrease the frequency from 50 hertz up to 49.78 hertz, and here is the step size, which is minus 3 millihertz. The DT is 200 millisecond, which is enough for the pickup value or to test the pickup value of the under frequency stages. And also in ramp 3 we will ramp up the frequency again from 49.78 up to 50 hertz by step size equal to 3 millihertz to get the drop off value of the under frequency protection. And here is the detailed view for the analog output of the 3 channel, and we are injecting the nominal value of the voltage at all states. And also the binary output here, there is no need for simulating any binary output such as circuit breaker close command in this case. On the other hand, while testing the over frequency protection or frequency over stage 1, the test universe ramping module also is used to gradually increase the frequency until the relay operates at its backup value. And as with the under frequency test, also the start signal of the over frequency stage 1 must be mapped to the binary input. So you can see here also ramp 1 and ramp 4 have the same nominal frequency just to reset the relay. And ramp 2 we can ramp up the frequency from 50 hertz up to 50.20 to 100 millihertz, with a step size equal to 3 millihertz, and the DT is 200 millisecond. And here is the trigger condition: the start will be changing from 0 to 1. And on the other hand, ramp 3 we can ramp down again from 50.22 hertz up to 50 hertz with minus 3 millihertz as a step size. And the trigger condition here, the start will be changed from 1 to 0 to get the drop off value of the over frequency protection stage 1. Also, you can see the ramp assessment here for the backup value and the drop off value for ramp 2 and ramp 3 respectively, and also the conditions of the start contact from 0 to 1 and from 1 to 0 respectively. So you can compare the actual values with the nominal values, and you can set or you can assess this result based on the allowed tolerance or allowed deviation based on the relay technical specification. On the other hand, while testing the trip time delay, as you can see, of the over and the under frequency stages, the test universe test sequencer module is used in this case to verify that each stage operates within the configured time setting. So the trip signal of the over or under frequency stages must be mapped to the binary input to capture the relay response time. And in the test sequencer, the test modules run each stage sequentially. And you can see here state number 1 representing the healthy state with the nominal voltage and nominal frequency for 2 seconds, just to allow the relay to be resetted and to be armed for the next state. And state number 2 we will test the under frequency protection stage 1. So we will inject also the nominal value of the voltage, but with a value of frequency under the set point. And also the time, it can be 1.5 from the expected trip time. So we are expecting it 20 seconds. So we can put it 30 seconds just to be long enough to detect the trip time. Also, state 3, it's healthy again, just to reset the relay with the nominal voltage and the nominal frequency for 2 seconds. Then state 4, we can test the over frequency protection, as you can see. So we can inject the nominal voltage and the frequency to be higher than the value of the set point for time delay equal to 1.5, the expected time delay, so to be 30 seconds. And state 5 again to be healthy, just to allow the relay to get to the reset state. So finally, you can evaluate or document the measured trip times. The corresponding test report also should be defined and generated from the measurement view, as you can see here for the state sequencer module. Now we will talk about testing the stage 2 of the under frequency protection. So we cannot use the ramping module, so we will use a pulse ramping module in this case to verify the relay fast trip response at deep frequency drops. So the trip command in this case for the under frequency stage 2 or over frequency stage 2 must be mapped to a binary input to record the relay operating time during the test. So it's important also to keep the nominal voltage applied throughout the entire test sequence to prevent the unintended operation of the under voltage protection or blocking of the frequency protection. Also, additionally, there is one key point to note that the drop-off value of the under frequency stage 2 cannot be measured with this module. So since the pulse ramping test only triggers based on the trip command transition from 0 to 1 or from 1 to 0, but we can only test the backup value of the stage 2 here. And also the test ensures the relay reacts correctly and within the expected time when a severe under frequency condition occur. So you can see here the pulse ramping. You can from this is the start point to this is the end point of the pulse ramping, and also here is the pre-fault time, which is set to 5 seconds, which is long enough to reset the relay and to simulate the pre-fault case or the pre-condition case. And also we have the step size to be 3 millihertz or minus 3 millihertz in case of the under frequency stage 2 protection. The reset time to be 5 seconds, which is long enough to reset the relay. The fault time should be long enough, more than the expected trip time, which is already 10 seconds, so we can put it 13 seconds. So here at the end of the day, you will have the reset state, so there is no need to the binary trigger conditions because this is the nominal values of the voltage and the frequency. But in the fault stage, we will take the trip command change status from 0 to 1 as a binary trigger condition, and the nominal value which is expected is 47 hertz with a tolerance 10 millihertz plus or minus, and you can see the assessment level here using the pulse ramping module. On the same way also, while testing the over frequency stage 2 pickup value, also we can use the pulse ramping, as you can see, to verify the relay fast trip response at higher frequency condition, and also the trip command in this case will be mapped to a binary input, so we can assess the relay response time accurately, and we can record it also during the test. So here is the main difference. Here is the start point, which is from, so we will start from 51.97 hertz up to 52.02 hertz, and we are expecting 52 hertz, which is a set value of the over frequency stage 2 protection. And here is the delta, which is a step size called equal to 11 millihertz, and the fault time also to be long enough and more than the expected trip time. So 13 seconds is more than 10 seconds, which is more than enough to get the trip time or to get the pickup value of the second stage of the over frequency protection function. Now we will talk about testing the time delay of the over frequency or under frequency stages 2. So we can use the state sequencer module as we explained in the stage 1 to verify each stage trip within the configured time setting. Also, we can make the same local hardware configuration. So we need 3 voltage output as we explained. As a phase neutral voltages, we need the trip command of the over and under frequency stages 2 to be connected to the CMC binary input. And also, the state sequencer will test each stage sequentially as explained in the first slide, but here we will test only the second stage of the over and the under frequency. So state number 1 and state number 3 will be represented to the healthy states with the nominal frequency and nominal voltage for 2 seconds, just to reset the relay to be armed to the second or subsequent states. And also we have the state 2 representing the under frequency stage 2. So here is the test frequency 46.98, as you can see, which is less than the set point, and the time will be 1.5 the expected trip time. So the time setting is 10 seconds, so we can set it to 15 seconds, which is long enough. And the trigger condition here to be taken with the trip contact from 0 to 1. Then state number 4 also we can simulate the over frequency stage 2, so we can simulate the 52.02 hertz, which is enough to get the trip time of the second stage of the over frequency protection. So you can see the time assessment of both stages. So the state number 2, we can simulate the start of the under frequency protection and the stop with the healthy 2 or with the trip contact from 0 to 1, and the T nominal is 10 seconds. Here is the T actual. Also in the same way with the over frequency stage 2, in the same way also we can define the actual time. We can define the assessment based on the tolerance of the trip time. Last but not least, now we will talk about testing the minimum voltage value using the over frequency stage. So in this test, we can use the over frequency stage 1 to verify the relay response as the defined voltage limits. So in the test sequencer, we can define one test point above and one test point below the tolerance range to evaluate the relay performance. So you can see from here the healthy 1 and the healthy 2, which is the state number 1 and state number 3, used to safely reset all the trip commands after each step. And also during this test, the under voltage protection function is plugged by the circuit breaker open signal, which is the generator circuit breaker high signal, so to prevent any interference. So finally, to properly assess the relay operation and trip times, the corresponding test report should be defined in the measurement view, as you can see. So state number 1 will be healthy, state number 3 will be healthy with nominal frequency and nominal voltage, and we have this value which is available in the relay Siemens relay 7UM parameter setting, which equal to 65 voltage. So in the phase 2 ears value will equal to 37.527 volt. So you can see this value, state number 2, the V test is equal to 0.98 multiplied by this V minimum, so equal to 36.78 voltage. And also state number 4, we can inject 1.02 multiplied by the V minimum, which equal to 38.28. So in the state number 2, there is no any trip happens, so we can measure this time, which is 30 seconds fully without any trigger happen from the contact. And on the other hand, in state number 4, because we are injecting 1.02 multiplied by the minimum voltage required for operation, so we are expecting the over frequency stage 1 to be operated after 20 seconds. So, and here is the actual time measured in this case. So thank you, and stay tuned for the next video.